Hopefully you managed to try to prove this particular sequence formulating the Deadlock Freedom proof obligation. And did you manage to prove it? I presume the way you did it was by considering the inference rules that we actually covered last week, about the 10 different inference rules. They're pretty easy, but they're also very useful. However, it might turns out you just cannot really make complete progress. Remember, every time you want to prove a sequence, the process will always be starting from the original sequence, which may not be automatically provable. So you will have to somehow transform that particular sequence into a set of sequence. And the way we do it is by using a tree structure. And you definitely see the more like a tree structure this week. Last week, the proof was rather straightforward. It's more like a linear structure, more like a linked list, basically, for all the sequence. But for this week, you're definitely going to see the tree structure. But eventually, at the bottom level of the trees, we want to make sure every sequence at the bottom, like a leaves over there, is automatically provable, matching some axiom rule for the inference rule. That's something we'll see always. That's something we'll aim to achieve always. And what I would like to do now is to really expand this small example set of inference rule to be something that will be relevant to our proof for the Deadlock Freedom rule over here. That's what I would like to do now. Okay, let's take a look. And we got 2 slides over here to show. We got 6 more rules to really show, introduce to you this week. That'll be enough for the Deadlock Freedom proof. Right. So the first slide, I would like to talk about these 4 axioms. Let's go over one by one very quickly. Let me just present the slides, and I'll make some annotation on this iPad page as well. Right. The first one is called hypothesis. So this is to say, if you want to prove something, and if that something can also be assumed, then that P is already automatically proved. Right. That's the first one. A goal is proved if it can be assumed. It sounds very straightforward, right? But it will be incredibly useful when we get to the actual proof for the Deadlock Freedom. Of course, not just for Deadlock Freedom, but it's going to be for any sequence that will be applicable for this rule. The second axiom rule will be the false on left. So again, the L over here, you can see the L over here simply means the false over here. So sometimes people call this bottom, right? And for true, symmetrically called the top. Right, but that's a mathematical symbol for false. And of course, sometimes you may also see we spelled it out literally, F-A-L-S-E. That's fine too. Right, so you can see the false appears to the left of the turnstile. So this is why you see the L over here. Right, just understand the naming for the rule. And so here we are saying that if we assume false, right? Remember the formal meaning for turnstile. It simply means implication. So we basically got false implies P, which will be true always. So there's nothing else to prove, right? So assuming false, anything can be proved, right? It's straightforward. And also we got the true. In this case, the true appears on the right of the turnstile. You can see the true over here, right? Well, what's going to happen in this case? So that'll be equivalent to P implies true. In this case, what's going to happen? P implies true. Assuming P, are we able to prove true? Well, actually, true can be proved always, right? So true is proved regardless of the assumption. So true is really the tautology that can always be approved regardless of any assumption you make. You can make any assumption you like, or you can even make no assumption, but true can just be proved anyway. The final axiom rule will be EQ, just for equality. Okay. So we are saying that regardless of any assumption, P over here to the left of the hypothesis, if you simply just want to prove E is equal to itself, it can always be proved, right? So you can say something is always equal to something itself without any assumption, right? So an expression being equal to itself is actually proved regardless of the assumption, right? It's very similar to when you try to prove the true over here, right? Because E equals E is can be definitely be reduced to true, which can be proved automatically disregarding the assumption. Right, so that's these are the axioms which I would like to talk about, and let's now just go move to the iPad page and make some annotation quickly. Right, I kind of put the other 2 rules which will be on the next slide together, but you can, for now, you can just forget. You can just ignore these two rules just for now. All right. So let's now look at 1, 2, 3, and 4 very quickly. Okay. One thing to note is you can see for all the green ones, which I might call a convention for axiom rules, right? I just call them axiom rules. Axiom inference rules over here. So that simply means if you actually got a sequence of this particular form, in order to prove it, it will be sufficient to prove nothing, meaning that the sequence over here is automatically proved, right? Let me just make that annotation very quickly, right? So you can see this part over here is simply just empty, right? So what does that mean? That really means to prove the consequent of the inference rule, it is sufficient to prove nothing, because the antecedents of the inference rule is simply missing. And if I say it is sufficient to simply prove nothing, that means the consequence is automatically proved, right? That's really what it means. I'm just trying to help you recall the definition for the inference rule, and you really want to understand what does it really mean when the antecedent part here is simply just absent. That means the consequence sequence can just be discharged automatically without any further justification. Okay, i.e., consequent proved automatically. All right, so that's a very important recall about the definition. To prove the consequence, it is sufficient to prove nothing, right? That means the consequence is proved automatically, right? Very important remark. And similarly, well, let's actually, before I do that, okay, let's say here we are saying that if the hypothesis also appear as the goal to really prove, that means assume something, you want to prove exactly that thing you actually assume. In that case, the whole sequence is automatically proved, right? And you can try to relate this to your predicate logic quickly, right? We know that in our predicate logic, if you say, definitely you can say, for example, H and also P. So whenever you got comma over here, as we said before, that means you got different hypotheses conjoined together. So this really means conjunction, right? H implies P, right? So you can see here, the hypothesis simply appear here and also here. So this particular implication is simply just proved without any further justification, right? So this one over here is definitely a theorem without further justification. And it would be similar reasoning for all the other three axiom rules, but let's just go over them very quickly. Okay. And what about the second one? The second one over here is saying that if you got a sequence of this particular shape, in that case, it's proved without any further justification because the antecedent is actually empty, right? For this one here, how do we understand it as a predicates? Well, so if you remember in predicate logic, it's called the zero of implication, right? So if you say false implies P, right? It's always true. It's equivalent to true, right? So here we call this the false and this the true, right? Let me just annotate it very quickly. This symbol over here is really false. And sometimes mathematicians would like to call it button. Right? You can see the way you draw that is more like a button, right? Something like that. And symmetrically for this symbol over here is really denoting true. And sometimes people also like to call that top, right? The way you draw that is like a top over here as opposed to that, right? So these symbols, you should really recognize them as well, just in case you see them in other rules. Right, so this part over here is really the zero of implication, right? Zero of implication. And symmetrically, just one more thing before I talk about the symmetry. Okay, you can also see that over here, when we say L over here, L really means that the false that we are considering appears to the left of the turnstile. Symmetrically, the R over here really means the true that we are talking about appears to the right of the turnstile, right? That's something I also explained in the earlier rules. They follow the same naming convention. And how do we interpret this rule as a theorem? So, as usual, we're going to interpret the turnstile as implication for sequence. And for this one here, it's going to be P implies true is equivalent to also by the zero of implication. Zero, well, meaning that you're going to get just true always, right? So this is also the zero of implication. So there are two variants of the zero of implication, either because the hypothesis or the hypothesis over here is actually false, or the consequence over here, or the goal over here is actually true, right? Either way, right? You want to understand this pattern over here. So either the hypothesis is false, or the consequence over here is actually true, right? The goal. All right. Right, so that's about these axiom rules. Oh, actually one more, I just forgot. All right, over here, this is also important. This is also straightforward. You can think about this part over here, any expression E be equal to itself. By the way, this is not Java assignment, right? It's mathematical equality, right? This can simply be reduced to true, in which case we just go back to this particular axiom rule. So we're just creating this also for convenience. You can think about this is more like a special case of this, because whatever we have as the goal for the sequence can be reduced to true. All right, so these are the axiom rules, and hopefully you're feeling comfortable with them, and they are incredibly useful for our deadlock freedom proof, as we'll see. Right, so that's the first slide for the example rules. Let's see the second slide. Okay, so I got two non-axiom rules for you to consider, right? We got one, and also we got two over here. They look very similar over here, but I think I'll leave you to really read the description over here. It doesn't really, it's not very effective if I simply read it off. But also watch out for the color I actually use over here for the green and also for the red. Green is for the left hand side expression to the equality. F is actually, the red is actually for the right-hand side expression of the equality. I'll just make there's a tip for you to really read the text. Make sure you really understand the text. I try to be very careful about writing them so that you can understand the rule, hopefully completely. All right. So read about these two. They're completely symmetric to each other. And at the same time, let me try to do some illustration to help you. All right. So let's try to understand first of all this one over here. When we say LR versus RL, what does that mean? So that means we're going from left to right. Okay, so think about the way to interpret this is to say from left to right. From left to right, or even more precise, replace occurrence of left by right. So that's what we really meant by from left to right. And so that means you want to replace the occurrence of left by right. So let's see exactly what's going to happen. So don't forget about the meaning for inference rule. When we have an inference rule over here, in order to prove this sequence over here in the consequence, it would be sufficient to prove this sequence over here and the antecedents, right? That's the meaning to start with, okay? And in the consequence over here, we already have one of the hypotheses to say E is equal to F, meaning that we can substitute one by another. But which direction should we go? Should we say we want to substitute E by F? That will be from left to right. Or should we actually substitute F by E? So that will be from right to left. So that's exactly what this rule is about, but I'll get there, right? Once you understand this one here, the other one will just be symmetric, okay? So what we want to really highlight is about this part over here, right? So this is part of the hypothesis. This is one hypothesis, meaning that E and F are interchangeable. Right, so let's see exactly how that would go, right? So here we are saying that E is exactly equal to F. So what we'll do is, you can see here in the goal over here, we're actually expressing the property in terms of the E. You can think about the goal P that we want to prove depends on the expression E, right? And also there might be some extra hypotheses in the same sequence in which they also depend on E over here, right? So far the sequence originally we wanted to prove, we actually got some hypothesis and also we got some goal, and each one of them actually depends on the expression E. And we got some extra hypothesis telling us that there is another expression F, which is equivalent to E, in which case it would be sufficient to prove exactly the same thing, H and P over here, but we're going to replace E by F, and we still keep the original hypothesis equal to F, right? That's exactly what we're doing, right? So what I want to annotate once more would be, you can think about to go from E to F over here, and also to go from E to F over here, we actually back up by the assumption that, or by the hypothesis that E is exactly equal to F, right? That's exactly what we have. That's something I would like you to really make a note over here, right? When you actually go from what you want to prove into what would be sufficient for you to prove. In that case, you go from E to F. You go from E to F. In that case, it will be from left to right over here. We are simply replacing every occurrence of E that we want to prove into F so that we know what will be sufficient for us to prove. All right, hopefully that's enough explanation of for you, right? You really want to see that visually, right? Let's do one more illustration over here. And what about this one over here? This one over here is going to be symmetric. So we say from right to left, right? So this will be from right to left, meaning that you're going to replace every occurrence of the right-hand side of the equality by the left-hand side of the equality, right? How do we do that, right? So there's something you want to isolate just to make sure you understand it. So the same hypothesis is going to appear on both the antecedents and also the consequence of the inference row. Let's start with that. And then in what we are supposed to prove over here, the property and the hypothesis, they both depend on F, right? You can see they both depend on F over here. And we got the extra hypothesis telling us that F is actually equivalent to E. So now what we're going to do is we're going to go from right to left over here to really say we're going to replace every occurrence of F by E, given the hypothesis that they are equivalent, right? So we're going to go from F to E, and also we're going to go from F to E, right? So this is given that E is equal to F. And you can definitely see that over here, right? So once we have done that, you can see go F to E and also F to E over here, right? The rule itself is not so difficult to really understand, but you really have to make sure you know which one to really use. So if you want to replace, basically this is what you want to watch out for, but we'll definitely see that when we try to prove the deadlock freedom example. Whenever you got in your hypothesis some equality over here, so you will know that the left-hand side may be replaced by the right-hand side, in which case you're going to use this rule. Or alternatively, the right-hand side may be replaced by the left-hand side, in which case you might use this rule instead, depending on which one you want to use. Of course, in case what you want to prove over here depends on the left, in which case you definitely want to replace the left by right, right? Maybe. And in the case where what you want to prove is actually depending on the right-hand side over here, in that case, you may just want to replace the right by the left, right? That's kind of the insight into the inference rule. But exactly when to use it, you have to judge. All right. Hopefully that's enough for you to at least get some intuition. All right. So now I would like to conclude this part of the lecture just by presenting an exercise for you. And I would suggest don't really go to the next part of the lecture until you actually try to do this exercise. Grab a piece of paper and then get your pencil, get your eraser, whatever. Just get it ready. And also, I want you to also get yourself handy for this inference rule that we just newly talked about, you can also download it from the course lecture site. I also made a standalone clean PDF for you, but this one just an annotated version, just in case you got confused, or in case you forgot about the details. I want you to have this example rules ready, and also the previous one, which I also spoke about, right? The previous example rules that we spoke about with the increment, decrements, monotonicity, the OR, R1, the OR R2, and etc., right? With that one as well. And I want you to now consider this single sequence formulating the deadlock freedom proof obligation. Are you able to actually prove this or discharge the sequence over here using the two sets of example inference rule that we have already covered? Right? Are you able to do it? If you're not able to, can you go as far as you can so that most of these sequence may just have been discharged using the axiom rules? Maybe some of them may not be, right? At least that's what you should do. If you cannot just look at that and say, oh, I don't know how to prove it. You really want to try. That will be something that you will be given in either the test or the exam. So that's really something you want to practice. Right, so I'm going to end the video right now, but I would suggest before you move on to the next video, try this exercise over here to see how far you can really prove it. And that will definitely give you some more insights into the model itself. All right, I will see you in the next part.